All right, guys, chapter 8, if you look in the top right-hand corner, it says sequences and series. Okay? Sequences, in my opinion, is just kind of another word for pattern. All right? We've been dealing with patterns since elementary school. Okay? And it's a pattern, a numerical pattern. All right? So we will talk about sequences and series. Our objectives today, we're going to use sequence notation to write terms of sequences. We're going to write a rule for the nth term of a sequence. All right, and we're going to sum the terms of sequences to obtain a series and use summation notation. Okay, now first of all, what is a sequence? A sequence is an ordered list of numbers. I said before, it's basically a pattern, a numerical pattern that we can see trends with and find the pattern rule and so on. Okay? Now, we have finite sequences and infinite sequences. Well, infinite means it goes on forever. All right? Finite means there's a certain number. So a finite sequence is a function that has a limited number of terms. It will not go on forever. Okay, an infinite sequence is a function that continues without stopping. And whose domain, which we've talked about domain a lot, domain is all real numbers. I should say all positive. This should be is too, not are. Typo there. Whose domain is all positive integers. Okay? Domain in range, slightly different when we're talking about a sequence. The domain is the position of each term in the sequence. Okay? For example, if I have a sequence that's like this, I'm just going to make it up. Okay? If that's my sequence, well, this is the first number in our sequence. Okay? This is the second number in our sequence, the third and the fourth number. All right? So the blue numbers would be essentially our domain because it talks about the position of each term. All right? The range would be the ones in red. Those are actually, those would be our range. So this is the terms. So the blue numbers are our domain. It talks about the position. The red numbers are our range, and that actually talks about the terms or the numbers of our sequence. Okay, so a sequence. It has domains, like I said before. It's going to be like we're going to have certain numbers in our sequence. So the domain talks about the position of each term. All right, and our range is the number. Okay, is the number associated with that position. So going back to this example, the blue numbers are my position. The red numbers would be my actual terms. So as a general form, this is what we call a sub 1. It's the number associated with being in the first position of the sequence. Okay, this number, whatever number this is, would be a sub 2. It's the second number in our sequence, and the pattern continues. A sub 3, a sub 4, a sub 5. All right, we have finite sequences and infinite sequence. So if a finite sequence means it ends. So for example, again, just making this one up, 2, 4, 8, 16, and it stops. Okay, that's finite. It has an end. Okay, and infinite would mean that it goes on forever. So for example, 2, 4, 8, 16, and then it would be represented by this dot, dot, dot. It's going to go on forever. That pattern will continue, and it will never, ever end. All right, example 1. Writing terms of a sequence. It says write the first 6 terms of the following sequence. Okay, so here's our sequence. Okay, this would be a linear pattern like we've seen in Algebra 1 or in this class. Well, if we want to find a sub 1 or the first term in this sequence, we're going to plug in 1 for n. So if I plug 1 for n, 2 times 1 is 2, this would be 7. If I want to find a sub 2 or the second term in the sequence, we're going to plug in 2 into our rule. Plug in 2 there, what do we get? 9. If I plug in 3, what do we get? 11. I think we see the pattern. What are we doing? Going up by 2. Now, kind of making the connection back to Algebra 1, this is like slope-intercept form, isn't it? Where this is our y-intercept or our starting value. Okay, and this is our slope. So we're going to increase by 2 every time. So this is going to give me 13, 15, and 17. So given the function rule, we're able to find the terms of the sequence. Questions on that? All right, going over this next one. So I need to plug in 1 because we want to find the first term of our sequence right here. What's 1 minus 1? 0. What's anything to the 0 power? That's 1. So a sub 1 is 1. The first term in this sequence is 1. All right, if I plug in 2, 2 minus 1 is 1. What's negative 3 to the first power? Negative 3. Negative 3 is the second term in the sequence. If I plug in 3, 3 minus 1 is 2. What's negative 3 to the second power? Positive 9. Plug in 4. 4 minus 1 is 3. Negative 3 to the third power? Negative 27. When we have an odd exponent, all right, it's going to be negative in this situation. 5 minus 1 is 4. Negative 3 to the fourth. That's an even exponent, so it's going to be positive. I think that's 81, right? 81, and then is this negative 243? Okay, so this is the first term in our sequence, the second term, the third term, the fourth term. That would be our domain. That's the position, all right? And the red numbers would be the actual terms of the sequence. Okay, something that I need to cover in order for us to do our assignment online that isn't in the book, so it's kind of goofy, is talking about 2 different types of sequences. So actually go back to the bottom of your front page. I'm sorry, because I think this is the best place to do it. There's 2 different types of sequences that we're going to talk about. The first one is called an arithmetic sequence. Okay, an arithmetic sequence. That means an arithmetic sequence is when we are going up or down by the same number. Okay, so we are increasing or decreasing by the same number. And that's why I put it over on the left, because if we look over here, I'm going up by how much every time? I'm going up by 2. That's an arithmetic sequence. Going up by 2, going up by 2, going up by 2, going up by 2. Okay, the other one is called a geometric sequence. Now, if I look at this example, this one over here on the right, am I going up or down by the same number? Well, here I went down by 4, there I went up by 12. Okay, so we see that it's not consistent, it's not linear, if you will. All right, a geometric has the same ratio when you compare 2 terms. So for example, if I were to compare these 2, my ratio would be 1 over negative 3. Would you guys agree there? Or negative 1/3. That's the ratio from one term to the next. If I were to do the next 2, well, that would be negative 3 over 9 Well, doesn't that reduce to negative 1/3? Negative 1/3? Absolutely. If I were to do 9 over negative 27, doesn't that reduce to negative 1/3? And so on and so forth. So this example on the left is arithmetic, meaning it's linear. It's going to go up by the same thing. All right? This is not. Now, the concern here is people see, oh, this is negative 1/3, negative 1/3, negative 1/3. Or I guess you could say maybe negative 3, negative 3, negative 3. And they think this is going up by the same number. But would you guys agree that this is not growing by the same number every time? It's increasing at different rates. Okay, so on our assignment today, we're going to have to recognize sequences as either arithmetic, geometric, or neither. Well, if it doesn't do this, and it's not doing this, then it would be neither. Okay, top of the next page. Example 2, it says for each sequence, write the next 2 terms and write a rule for the nth term. Guys, this stuff's so hard to teach. Okay, there's really no way I can teach it besides just doing examples. Okay, so if we look at this first example, some people are going to see these patterns like this. Other people, you could sit there for probably 2 days straight and not pick up the pattern. That's just kind of the nature of these things. So I'm just going to give you 30 seconds. Look at the pattern. Actually, I'm going to give you a second to look at the first 2. This one right here and this one over here. I'm going to give you 2 minutes to try to find the pattern first. All right. Second, find the next 2 terms of the pattern, and then try to find a rule for the pattern. Really, if you can find the next 2 terms and find the pattern, I'll teach you how to do the rule. Okay? Go. Let's talk about this. This is the first term in our sequence. So I'm going to put a 1 here. That's 2. That's the second term in the sequence. That's our third term in the sequence. And that's our fourth term of the sequence. So somehow, this is like our n. We need to get from this number to these numbers. Do we recognize anything about negative 1, negative 8, negative 27, negative 64 that just kind of stick out at us? They're all negative. I agree. What else?
Can't they all be cubed?
What's that, Sam?
Can't they all be cubed?
Oh, they're cubes? Is that what you mean? 8, 27, 64, are those all cubes? Do you guys see that? Yeah, they're all cubes, all right? And on top of that, they're all negative. Okay, so 1 cubed is 1, all right? 2 cubed is 8, 3 cubed is 27, 4 cubed is negative 64. What's the next 2 numbers in our sequence going to be? What's that? Negative 125, I think that would be the next one, and negative 216. So this is our 5th term in the sequence, and that's our 6th term of the sequence. So somehow we have to get from n, this number, to that number, thinking of a rule. So how do I get from 3 to negative 27? We cube it, right? Tristan said, don't we cube it? But then we'd also have to make it negative. So the idea is that I want to write a function rule. I'm going to call it a sub n equals, and make a function help us to get from n, our domain, to our terms or our range. Now, sometimes it's just best for me to maybe show you, and then you'll kind of, oh. Now, I think this one is this. Because if I just do this, if I just do n cubed, does that work? No, it's got to be negative, right? So we need to flip our n to be negative. So I think there's a couple ways to do it. I think one of the ways is to do this. So if we take our n, which is these small little numbers up here, and we make them negative first, then we cube them, we'll get to that. I think another option would just do this. Because if you cube it, then make it a negative, it doesn't really matter in this situation. So here is our rule to find the nth term, meaning, hey, I want to find if this, in this pattern, I want to find the nth term, meaning maybe the 100th term in the sequence, or the 1000th term in the sequence. I now have a rule, or an equation, if you will, to help me find whatever term I wanted to find in the sequence. Are there questions on that one? Okay, let's look at this guy. So this is the first term in the sequence. That's the second term. That's the third term. That's the fourth term. So to get 1, start with 1 to get to 0. Well, I can minus 1. But then minus 1 doesn't work for down the line, does it? Say it again? It's going up by 2s. Okay, so we're going up by 2. We're going up by 4. We're going up by 6. Okay. So what are the next two in our sequence? 20 and 30. Is there a way we could write that into a function rule? And I didn't see that the way you just said. I didn't see it, but it makes sense. It's true. I think there are a couple ways to do some of these. And so I didn't know if there was a function rule to do that. Here's what I saw. I saw that 4 times 3 is 12. You guys see that? And 3 times 2 is 6. See that? And 2 times 1 is 2. And 1, what's before 1? 0. 1 times 0 is 0. So to get this number, we need to take this, which is n, and times it to get 12. I took that number, which is n, and times it by 3, which is 1 less than n, isn't it? So it's n times n minus 1. And I think that works for all of them. So to get the first term, take 1 times 1 less than 1, which is 0. 1 times 0 is 0. To get our second term, take 2 times 1 less than 2, which is 1. 2 times 1 is 2. To get to 6, take 3 times 1 less than 3, which is 2, to get to 6. Is there a way that we could do it the way you said it, Autumn? Autumn said we're growing up by 2 every time. So the amount that we're increasing is going up by 2. I don't know. I'd have to think about that. The book had it this way. There might be a way to show that. Mr. Wen, any ideas on how to?
Maybe make the slope like n plus 2, and then the starting value would be 0.
Starting value would be 0. And this would be n plus 2. Yeah, I don't know. There might be a way. I just don't want to take all you guys' time me thinking about how to do that. Do this one on your own. Just what do we observe about this pattern, guys? This sequence. Tristan says it goes up by 2. What does that tell? Back to the bottom of the front page, is that arithmetic or geometric? That is arithmetic. It's going up by the same amount every single time. Guys, if it goes up by the same number every single time, that's like a linear function. It's going to be like y equals mx plus b. So a sub n, let's find our next two numbers first. This has to be 11 and 13, right?
Yep.
n plus 2. Is that what you're saying, Tristan?
Yeah.
Now, I walked around and I saw some n plus 2s. Check it. We have a rule. Let's see if it works. And I think it's imperative, guys, that we write these numbers up above. Because I'm trying to get from this number to that number. So if I plug in 1 here, if I plug 1 in here, 1 plus 2 is 3. That works. If I plug in 2, 2 plus 2 is 4. That doesn't work, does it? So we can try these. Now, I'm just letting you know, if it's arithmetic and we're going up by 2 every time, that is the slope. Where's the slope on this? That's m, right? So we need to have a 2 here. Does that make sense? Our slope's 2. We're going up by 2. That needs to be where our slope is. Now, this is our y-intercept. So this is the value. This is our y value when our x value is 0. If I were to continue my pattern but go that way, what's this going to be? Sam? It would be a 1. So 2n plus 1, I think, is the correct rule here. Our slope is 2, and if I went back to find the 0 term, it would be 1. Again, we can try it. Plug in 1. If we plug in 1, we'll get 3. If I plug in 2, we'll get 5. If I plug in 3, we'll get 7. If I plug in 4, we'll get 9. Questions on that? Okay, what about this next one? Think about that for a minute. Go. First, let's talk if it's arithmetic or geometric or neither. Does it increase by the same number every time? No. The ratio, this would be 3/8. Does 8 over 15 reduce to 3/8? No, it doesn't. So it's not geometric, it's not arithmetic, this would be a neither. What do we observe about this? I don't need the function rule, but what do we observe?
Goes up by odd numbers.
Say it again?
Goes up by odd numbers.
Okay, we're going up by 5 the first time? 5, 7, 9. Okay, I totally agree there. Any other observations? Kim?
Like 1 times 3 equals 3.
Stop. Guys, if you're not writing these up there yet, you need to.
And then 2 times 4
I'm sorry, going back to where you started. Kim said 1 times
3 is 3.
1 times 3 is 3.
And 2 times 4 is 8. And then 3 times 5 is 15. 4 times 6 is 20. So you would do 5 times 7.
So 5 times 7 to get our fifth term, is this 35? Does that work with the way that you guys did it?
Yeah.
Okay, and this needs to be 6 times 8 to get 48. Does that work with how you guys did it? Okay, we've got those. Now we need to find a rule for that. I'm just going to let you guys know. And again, I was always kind of, in my mind, was always thinking the way that some of you guys are, we're going up by this many, and going up by this many, and going up by that many. But when you are increasing increasingly, that's kind of hard to think about as far as making a rule for it. Okay? So, my hint was that it's kind of like that. Now, going back to what Kim said. 1 times 3. Well, is it 1n here? And she said 2 times something and 3 times something. So we need to take n times something. Okay, and again, that's why I'm asking you guys to write 1, 2, 3, 4 on there. So we're always kind of going back to n. How do I get from n to this number? N times, what'd you say? To n times n plus 2. I don't know, let's check it out. So we did 1 times 1 plus 2. Well, 1 plus 2 is 3. 1 times 3 is 3. That works. If I plug in 2 here, 2 times 2 plus 2 is 4. 2 times 4 is 8. Hey, that works. 3 times 3 plus 2, that's 5. 3 times 5 is 15. 4 times 6, 24. 5 times 7, 35. 6 times 8. That works. So I think there would be our function rule. Guys, I'm not gonna lie, these aren't easy. And it's like if you don't like see them, it's hard to find them. Hopefully, if we do enough of these, we can start, recognizing how we did another one and maybe, figuring out that one. Use our notes when it comes to our assignment on these. Okay, moving along. Guys, I know I'm talking a while, but bear with me. Now we're going to switch a little bit and talk about a series. Okay, a series is the sum of the terms of a sequence. So now we're going to have a sequence, but we're going to be adding up all of the terms. Okay? Now there's some notation that we need to figure it out here. Now everyone watch me because I'm kind of picky here. This is sigma. It's a letter of the Greek alphabet. Can I show you something? It is not this. Okay, do you guys notice how the top and the bottom are like horizontal? Okay, I'm kind of being picky, but from teaching this before, everyone just kind of does it like this. Try to be a little bit somewhat neat, and these are horizontal. Okay, now that is summation notation. Okay, so it's sigma. Basically what this means is represents the sum of a bunch of terms. Okay, so we usually have a number, it usually looks like this, n equals 1. Let me just write all this up here. That would be, for example, what it could look like. Okay, now what is this thing? That is our lower limit. Essentially, that is what we're starting with. Okay, so for example, if it's n here, it will be n here. Okay, if it's x here, it will be x there. This is our upper limit.
Mr. Cole, on the bottom of the sigma, is it n equals 1?
Yes, sorry, did I write that too small? Uh-oh. Uh-oh. Yes, n equals. And this is our upper limit. And this is our rule. Okay, so this is our rule, or essentially the equation that gets us this pattern. And our lower limit, that tells us what we're going to plug in first for our n value. A lot of times it's 1. It doesn't have to be. Okay? It could start at 4, or it could start at 7 if we wanted to. And this is where we're going to end. So I guess you could say our domain, we're going to add up the first 5 terms in this sequence. We're going to plug in 1, and then we're going to plug in 2, and then we're going to plug in 3. We're going to add up all of those numbers. That's essentially what that means. Okay? And you'll see here once we start doing more of these. Now, if I were to write a sigma notation for this, there's sigma. First of all, what's my rule here? Again, be careful. What's n here? N is 1, n is 2, n is 3, n is 4. So if I take this plus 2, I'll get 3. But remember what I said, if I'm increasing by 2 every time, that actually needs to be my slope. So I think this is 2n. Because 1 times 2 is 2. 2 times 4 is 4. Or excuse me, 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. 4 times 2. Take my n values, times it by 2, and I'll get my terms of my sequence. Okay? So this is the first term in my sequence. So this would be n equals 1. Guys, if we're taking a pattern, taking a sequence, and writing summation notation for it, it'll always be 1 unless notified elsewise, otherwise. Okay? What's our upper limit? Not 8, but 4. That is our ending domain. Okay? So our lower limit, our upper limit talk about the numbers we're going to plug into the sequence. Okay, Okay, so that's how this could look. And a lot of this is just getting used to how things are going to look. Now, this is the same sequence as this one, but what's the only difference? What, Alyssa? It goes on forever, right? So I'm going to change things up. I'm going to put I equals 1. What's the difference between I and n? There is none. This just tells us, hey, what our variable essentially is. This could be k, this could be x, it could be I, it could be n, it could be anything. Hannah. If we are, not all the time, and I'll show you later when it's not, but if we are taking a sequence and writing it into summation notation, yes, it will be. But if they give us some summation notation, then it won't be. I'll show you that here in a second. But if we're writing it like we're doing, yes. What's our upper limit? It's infinity. It's never going to stop. We're going to go to the end. Yeah, there is no stop in the number of terms in this sequence. And then our function rule is the same, but instead of putting n, what do I need to put? I, because I've just put I there. It doesn't matter what you use as far as I or n or x or k, but you'll see a little bit of everything. Questions on this? Again, a lot of this is just new. It looks really weird. It's brand new. I don't think it's crazy difficult though. Okay, we're going to write summation notation. So draw sigma. To answer Hannah's question, if we're going to take a sequence and write it in summation notation, this will always be 1. That'll be 2. That'll be 3. Now, if there's ... here, that means we've skipped some things. So this is not 4. Okay? What number is this? Well, wouldn't 100 be number 4? We're going up by 25, right? So 100 would be 4, and then 125, 150, 175, 200, 225,
10.
250. So our upper limit is 10. So this needs to be, I'll do k, just to mix it up a little bit. K equals 1, and we're ending at 10. Now to find our rule. What are we going up by? Every single time. So I always said it would be 25, whatever our variable is, right? If we're going up by that, if we're going up by 25 every single time, it's going to be 25n or 25k.
Why wouldn't it be 25 plus k?
Because 25 plus k, if I do 20, to get here, it'd be 25 plus 1, which is 26, but that's not right. And that's it for that problem. We've created, from a sequence, summation notation. Over here. Actually, let's go down here once. We'll do that one in a little bit. So 1, 2, 3, 4. What's my lower limit? It'll always be 1. So if I use n here, you could use whatever. What's our upper limit? Infinity. What's our rule?
It's going up, it's 10 is up by 6 each time.
Okay? Here's what I would encourage us to do. If we could get away from the idea of it going up, or like Tristan said, and it's just it's timesing by 6 every time. Go from don't compare these two, but compare this one with that number. 2 to that number, 3 to that number. Or Tristan said, we're timesing by 6. So I guess repeated multiplication, timesing by 6, is exponents. What, Autumn? 6 to the n. Does that work? 6 to the first power is? 6 to the second power is? 6 to the third is? 216. That does work. Okay, so there's summation notation for that sequence. Let's do this one. We're starting at 1. I'll use I here. I equals 1. We're ending at, well, 1, 2, 3. I'm just going up by 1, aren't I? So 4 would be 8, 5 would be 9, 6 would be 10, 7 would be 11, 8 would be 12. This is 8. Is this arithmetic? It is, so that means it's going to be kind of linear. What's our slope? How much are we going up by? 1, so that means it's going to be 1n, which you don't really need the n, or the 1, but it's going to be n. Now remember what I said if we go backwards. What would this term be?
Big 3.
Aren't we going up by 1 this way? So going this way I'd go down by 1? n plus 4. Thank you. Yep, I know. It needs to be I here. What? No, this one's not too bad. What, Ralphie? Okay, here's our first term, here's our second term, here's our third term, here's our fourth term. So we're gonna start at 1, so n equals 1. That's our lower limit. Our upper limit is infinity. Goodness gracious, now what about this rule? I hate fractions.
It's n divided by n plus
And would you guys look at the numerators here? How does our numerator compare to n? Our numerator is the same, right? 1 and 1, 2 and 2, 3 and 3. So our numerator of this sequence is n. Whatever n, whatever the term in the sequence is, whatever that value, whatever, yeah, the number of term that is, that's what n is. That's what our numerator is. So how does our denominator compare to n? Ah, it's n plus 1. It's whatever n is, plus 1. Okay, now, I've said before that the sigma notation means add. So we literally want to add all these up. So the answer to this would be all of these terms added together. Okay, now, nothing's changed. It looks different, but you got to understand how I type it into the computer. I have to do it this way for some silly reason. So this really is k equals 4 and 8. Does that make sense? I just, for some reason, when you type it into the computer, it does this thing instead of this. So here's what we need to do. Our lower limit is 4. Now to answer Hannah's question, she says, is our lower limit always going to start at 1? Well, not if they give us summation notation. They can start whenever they want. But if we're taking a series to summation notation, it will be. So here's what we're doing, guys. We are going to plug in, we're starting at 4, so I'm going to plug in 4 for k. So if I plug in 4, what's 4 squared? 16. 16 plus 3 is 19. That is the first term in our series, okay? Or sequence or series. Now I need to go up 1. So instead of plugging in 4, I want to plug in 5. So when I plug in 5, 5 squared is 25. 25 plus 3 is 28. That's the second term in this series. Now I need to plug in 6. 6 squared is 36. Plus 3 is 39. Plug in 7. 7 squared is 49. 49 plus 2 is 52. Did I say the wrong number? Plus 3 is 52. And then plug in 8. Now 8 is where we're ending. That's our upper limit. 8 squared is 64. Plus 3 is 67. Take our calculators out, add all those numbers up.
So the 19 is the fourth, like, position.
Correct, yeah. 19 would be the 4th term in this series.
205.
Wait, 205?
C.
So that is the sum of that sequence or of that series. Same idea over here. Okay, we're starting at 1. We're ending at 5. So 8 times 1 is 8. Now we're going to plug in 2. 8 times 2 is 16. 8 times 3 is 24. Plus 8 times 4 is 32. Plus 8 times 5 is 40. Add all those up. What do we get? 120. Questions there? If I'm trying to find the sum, write them all out, add them up. Okay, now, there are 3 that I want to talk about that have kind of shortcuts to them. You guys like shortcuts, don't you?
Oh, yeah.
Okay, here's our rule. If there's a 1 here, whatever our upper limit is going to be n. We are adding up the first terms of a sequence. So if I'm going to add up the first n terms, well, so basically that means 1 plus 2 plus 3. Excuse me, I lied. Yeah, I'll just say it this way. If there's a 1 there, whatever our upper limit is, it's going to be there. This just means 1 plus 1 plus 1 plus 1. That's going to be our upper limit. Now, the sum of the first n positive integers. So this is 1 plus 2 plus 3, okay, is this. So if there is, whatever our variable here is, I, could be n, could be k, if that's here, here's our formula. N times n plus 1 divided by 2. And if we were going to add up the first squares of the first n positive integers, so if this is I squared, or n squared, or k squared, there's our formula. So 3 things you're looking for. I'll give you these on the test, but if this is a 1, if this is I, or n, and this is I or I squared, there's our formula. Okay? So if I look down here at our last 3, well, isn't this a 1? So our rule is that if that's a 1, the answer to this sum is our upper limit, which is 34. Okay? If this is k, well, that's kind of like our middle one here. Our formula is n times n plus 1 over 2. And n is our upper limit. So it needs to be 6 times 6 plus 1 is 7. So 6 times 7 divided by 2. 6 times 7 is 42. Divided by 2 is 21. The answer to that sum is 21. And lastly, if we have n squared, well, this one's a little bit more complex. It's n times n plus 1 times 2n plus 1 over 6. So what's our n here? N is our upper limit, which is 7. So 7 times 8 times, if I plug 7, 2 times 7 is 14. 14 plus 1 is 15. divided by 6. 7 times 8 times 15 and divide that thing by 6. 840. Oh, divide by 6. 140. Basically, guys, just so we understand, what this means is 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to 7 squared gets us 140.